Hey yo, what's up, everyone? It's your boy JOSHABRAHAM. We're continuing with sequence analysis. 1 hour. 1 hour! I seriously set a timer for 30 minutes. Let's go. You gotta do. Literally, my me. Did I just waste some time? Yeah, I did. So we were looking at the Markov model, hidden Markov model, right? Again, can we start this over? I looked into the H and I kinda understood works, but not fully. I don't know the equations. So let me know what is the objective of this question. And I believe this exercise is about detecting copy number variations in DNA using hidden Markov models. The main goals are identify the hidden state of each DNA segment, use observed data to infer these hidden states, observations intensities measured by the DNA microarray. Example x equals 8.70, 6.6. Incorporate the fact that the adjacent segments are correlated. Copy number changes are not random. If one segment is deleted, nearby segments are more likely to be deleted. Okay. HMM capture this correlation through transition probabilities between hidden states, how the matrices fit in, observation probabilities. I still don't get where do I start? What you're doing? You're essentially using the HMM to decode the hidden states for each probe based on the observed intensity values. The key idea: the true copy number is hidden, and observed intensities give clues, but they're noisy. HMM combines emission probabilities. How likely is this intensity gives a hidden state? Transition probabilities. How likely is it that the state changes between consecutive probes? Using these, you can infer the most likely sequence of the copy number. Equations you don't need to memorize yet. Mission probability of the probe xt given state ut. LinkedIn for sure, yeah. Not right now. What the? I hate it. The fuck? What's wrong? Ugh. Forward probability optional for understanding probability of observing the sequence up to the probe t, ending with the state ut. Viterbi algorithm. List the hidden states. Take the observed intensities. What's the observed intensities? We assume the probes of a segment with normal copy numbers emit an intensity with Gaussian distribution with a mean of 7, standard deviation 1 Armstrong, corresponds to copy number deletion corresponds to a probe with intensity nu1 equals 5.5, sigma 1 equals 2.0, segment with copy number amplification with intensities. I can feel my I can literally feel my attention span not working. Take the absurd intensities. These are okay. Okay. Looks like I didn't get a lot of said. How do I start this assignment? And figure out what so how do I start it? I kinda understood the hidden states, even though I don't know what that means on a physical scale, but I know they are numbers to represent observations. Probability of sequence of hidden states. Identify the day observed data. Probe intensities. Example x equals 8.7. Where is this value? Okay. This means we have observation vectors such as, okay, which where each of the entries corresponds to a measurement of one probe, and the probes are located on this order of the DNA. Hidden states, emission distribution, mean and standard deviation of each state. Create a table for each probe. Each xt. So I kinda understood value goes into this equation, but what's the t? Also, if you could, can you do one example of the resultant matrix? Right. One term in the matrix, so I know how the math is done. What t means in xt? T is the observed value of the probe t. T just indexes which probe in your sequence are you looking at. Example, if probe r, then x1. Okay, 1, 2, 3, 4, 5. Okay, so just move next round. Probe Gaussian formula ut equals j. Oh wow, 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 wow. Let's do the probe x1 equals 8.70 and hidden state 2. Normal. So 1 by sigma j root 2 pi of exponent. What is this new 2? We assume the probes of the segment of each normal copy number emit an intensity of Gaussian distribution with a mean of nu 2. Why standard deviation sigma 2 plus 1 Armstrong segment with the copy number deletion corresponds to a probe. How it fits in the emission matrix. Okay. From the question, I only saw and you used new to here. Could you explain why did you use that? And when are you gonna use the other one? In hidden Markov model for this problem, U1 represents the hidden state of probe T. For each probe, you don't know the hidden state. It could be 1, 2, or 3. There's no 3. Do we have a 3? Oh, there is. Okay. So, okay, how are these that's what I want. Not even readable. So okay, probe 1, probe 2. Okay. Hey yo, what's up, Devoted, for checking out the stream. I appreciate the checking out the stream. Hi, Josh. Yes, you called me. Who called? I don't know. I don't think I called. Absolutely. This is a 3 times 5 matrix. This is your emission probability matrix for the hidden Markov model. Here's what it happened. It's the emission probability matrix. Transition probability, emission probability. Each hidden state, which corresponds to the copy number, deletion fewer than normal copies. It's the probability of observing intensity of the probe if the segment is in the hidden state. High values indicate that the observed probe intensity is consistent with the hidden state. Probe 1 has intensity 870, normal state might have moderate probability. So high values indicate the observed probe intensity is consistent. So higher value downwards, or why it's important? This matrix is linked between observed and hidden states. Later algorithms like Viterbi or forward-backward will use it to figure out most likely sequence of copy numbers. Am I missing any lecture notes? I feel like I am missing something. Mm-hmm. 30 minutes. Profile, evolution, transition probabilities. Okay, we got some. Did I download this? Let me see if I have. No, looks like I don't. Do I have the multiple? No. I got pairwise alignment. Where's Scoring. Do I have scoring? Scoring. Yeah, I was for this one. Scoring part 2. Pairwise alignment. Okay, I don't think I've been here. Linear gap penalty. Pairwise alignment. Did I download this? Yep. So the one right after, multiple sequence alignment. Phylogenetics. Oh, that's the tree. Okay. Hidden Markov Model. Okay. At least we got the notes. At least we got the notes. Already 30 minutes. Okay, I don't know, Devoto did. I don't know if you're still on the chat. I'm gonna refresh the chat. It's better to look empty than not empty. It's cold. Fucking cold, brother. High values in okay. So let's say I have done this matrix. Now what would be the next step here? Once you have the emission probability matrix set up, the next step is to incorporate the transition probability, okay, between hidden states to model the dependencies along the sequences. Essentially, you are moving from observing single probe independently to considering the sequence of the probes and their likely copy number states. Here is a step-by-step path. So you're already set it to the transition matrix. Rows equals hidden. Rows are current hidden states, next hidden states columns. Each entry probability of transitioning from state I to j. Initializing starting probabilities, also given pi equals. Okay. Also given for the deletion normal amplification, this tells you the probability of starting in each state of the probe 1. This tells you the probability of starting in each hidden state at probe 1. Ow, that's kind of hurt. So the probability of starting in each. Apply dynamic programming. Do I have to though? Viterbi algorithm. Each probe, each hidden state S, multiply the previous best probability by the transition probability to the current state, multiply the emission probability for the observed probe intensity at the state, keep track of the maximum probability and path that gave it. This gives the most likely hidden state sequence of all probes. Backtrack. Calculate the probability. Transition matrix. Vertebrae table. Backtrack. Recover the sequence of copy numbers. Let me eat the stuff I cooked. Okay, can you explain what So looks like do the Viterbi matrix. Transition and so can you how is that step gonna look like, because the emission matrix is a 5 by 3 while the transition matrix is a 3 by 3 matrix. So how does it work? Is there a formula involved? I do have a lecture note on this, but it's a long one, and do you think it's better to refer that than asking you? Why am I asking ChatGPT if it's good to use ChatGPT? Stupid me. Yes, for this step, you're essentially using the Viterbi algorithm, which combines the emission and probabilities to find the most likely sequence of the hidden states. I can summarize it in a concise form. Emission matrix, shape 3 by 5, 3 by 3, stores the highest probability of any path indicating the state S at time t. Initialization t equals 1. Initial probability of the state S. Emission probability for the probe. Termination. Max probability. If you follow some, you can actually set up a vertebrae table yourself with the probes, 5 probes, x3 stages. So if you want, I can wait. How is the final matrix is gonna look like? Is it 3 by 5 or 5 by 3? Because you said both of them. The final vertebrate matrix is shaped 3 by 5 states X probes. So, okay. So, in this question, the answer is conversion of the emission matrix and the transition matrix emission to Victor or is there more? Because this question only has 0 points. It feels like it's a practice type of then so first let me know what's the if the we got 810, right? There's one more assignment. Assignment 10. Dude, it's not even a PDF. It's a Xcode. What the fuck? Yes, exercise 16, vertebrate matrix. This is essentially the answer. Exercise is more about practicing how to compute the emission matrix for the hidden. So I need to understand more on the understanding. Hidden Markov model. I still don't understand a lot. I need to understand. Installing components. What the fuck is this? God damn, we got 187 line of code. BioPython tutorial. Oh shit. Assignment 10 looks fucking crazy. Hidden states, observed states, initial states, state probabilities, transition probabilities, emission probabilities. Baum welch algorithm? Okay, I'll be right back. I gotta take a huge dump. I'll be right back, people. Okay. Back. How many minutes did I miss? Okay, could you how this one is gonna be done? You are asked to compute the probability of observing a oh god. Start with the initial probability for the first state of sequence. Example, multiply the transition probabilities for the subsequent states. Do the same for the sequence V, UV. Compare the resulting probabilities. The sequence with higher probability is more likely to be observed. So essentially, you chain together the initial probability and transition probability along the sequences. No Gaussian emission probabilities are used here. Okay. You know what? I'm gonna end the stream. I kinda understood. It's been 1 hour. I'm gonna keep changing the stuff in 1 hour. So I'm gonna end the stream. I just gotta call my parents. Quick call. We're gonna continue. Peace.